In this lesson, we will look at forward kinematics through homogeneous transformation matrices. In the earlier class, we have seen that two frames separated and rotated relative to each other can be related by homogeneous transformation matrix, and we can go on progressing from link to link, from the base to the end effector, and keep on and multiply the homogeneous transformation matrices H10 into H21 into H32 etc. up to H65. This result will be H60. That is a homogeneous there's a 4x4 matrix that will relate the frame attached to the end effector to the base frame. Like that, you can attach any two frames on the manipulator arm. But then in this, you'll find that a homogeneous transformation matrix has got 12 useful elements because the bottom row is not useful, is only dummy. But then even in the rotation matrix, there are only 3 independent variables because the squares of each column, which are direction cosines, or even the row of each row, sum of the squares will be equal to 1. And as such, that leaves only 3 independent variables. And similarly, the distance also has got x, y, z components, 3 independent variables. So there are only 6 independent variables, though there are 12 useful elements in the homogeneous transformation matrix. Well, we would like to now introduce the Dynamo-Tartenberg convention, which tries to, by imposing certain conditions, it will try to reduce the number of independent variables to just 4. Now, to do that, take two adjacent links. This is a link I minus 1 and a link I. Link I minus 1 is rotating, is moving about the axis Zi minus 2, and link I about Zi minus 1. Now, what we do is we draw common normal. We assign frames Zi minus 1 would have frame OI minus 1 on Zi minus 1, and how to choose the to locate it, what we do is we draw a common normal between Zi minus 1 and the previous Z axis. So, and call that as xi minus 1. So at this point, you got a frame OI minus 1, xi, Zi, xi minus 1, Zi minus 1, and YI minus 1. Well, similarly, we fix a frame by drawing a common normal between Zi minus 1 and Zi. So this frame Zi OI will be at this point on Zi on the common normal, intersection with the common normal, and we call that common normal as xi because this is the frame, and this frame is attached to this link I. This frame is attached to this link I, though physically they seem to be separated. They'll be rotating. This frame will be rotating along with this link I. OI minus 1 will be rotating along with this link OI minus 1, and so on. So this is the condition we impose, and there is certain flexibility at the base frame and also at the end frame fixed to the end effector. We can take advantage of that where if necessary. Well, now how to relate the idea? What is the idea now? Idea is to relate a frame OI minus 1 to frame OI attached to the respective links. To do that, you can see that there is we need to, well, one more thing is this xi, you draw a parallel to on frame at OI minus 1, you draw a line parallel to xi, and that angle from xi minus 1 to xi parallel is called the joint angle theta I, and that will be obtained by rotation about this axis. Okay. Similarly, you draw a line parallel to Zi minus 1 at OI. This angle from Zi minus 1 to alpha I about xi will be labeled as alpha I. Now, this distance up from OI minus 1 to the common normal, where common normal meets Zi minus 1, this intermediate point, the distance will be called di. The distance AI. In the if you travel from this point to OI, that is called the link length, and alpha is called the link offset, and this is called the theta I is called the joint angle. Well, the theta I, di, ai, alpha I will be now enough to completely describe the relation between this frame and this frame. That is what we used a Dynavit-Hartenberg convention for, or notation for. Well, how do we do that? Well, simply now for always for this a frame here to match with this, what are the transformations it has to go through? It has to turn around by an angle theta. Xi minus 1 has to go to xi. Now it will be parallel to this xi. It will travel to this point along zi minus 1. It will turn around by an angle theta I about zi minus 1 and will travel about a distance di on along zi minus 1. Well, these two we have seen in the earlier lesson. The two basic homogeneous rotations and translations can be clubbed into one homogeneous transformation matrix. The rotation of theta I about zi will be contained in this element cos theta minus sin theta cos theta 0, 0, 1. And this travel along this by a distance along z is represented as 0, 0, d. Okay, and of course this is the thing. So this is the HTM representing the relation between this frame traveling to this. Next, that frame has to travel to this so that the origins will be coincident. Not only that, Zi minus 1 and Zi minus 1 and Zi have to now also coincide. That can happen only if you twist around about xi by an angle alpha I. So it has got a translation and a rotation. They both along about x-axis. Therefore, we can combine both of them also into one HTM. And this is your cos alpha minus sin alpha 0 coming into this part of the rotation matrix is due to the rotation about x. And then, and in the last column, the movement is about AI on x-axis, so it occupies this position. So the rotation matrix is this is the displacement, and that describes this movement. Now we can multiply these two HTMs, and that the whatever matrix you get, that is going to relate this frame to this frame, and that will be in terms of theta, alpha, a, a and d. These two 4 parameters, independent parameters, describe the relation, and this is the homogeneous transformation matrix that relates two frames in in terms of the 4 parameters. We call them link parameters. Now, once we have, what we do now is, for a given robot arm, we write these 4 parameters and get a corresponding matrix H10. Write these corresponding parameters for this link with the next link, and then we call that as H21 and write a corresponding HTM. We can then multiply all those for link after link to obtain the necessary homogeneous transformation matrix. Well, we'll take an example. Suppose you have a cylindrical type of arm. You got a rotary joint, you got a prismatic joint which is moving like this, and a prismatic joint which will make the link move like this. So this is the end point to which your gripper, let us say, or some wrist or gripper will be attached. For the present, we will say it is the gripper attached to this point. We fix a frame there also. Okay, at the end of the gripper, at the end of the last link, we fix a frame. Well, to start with, we fix a frame somewhere in the middle. This is the inertial frame which doesn't move. As far as this analysis is concerned, we assume this O0 frame will not move as all the other links are moving in the robot arm. Well, how do we fix the various frames? Well, in this particular case, this is rotation about a vertical axis. So your Z0 will be about this, and the rotation, because it is a rotation, theta I is the joint variable. That joint variable will be theta 1. You have theta I about zi minus 1. Okay, the xi minus 1 to xi theta I about zi minus 1. That is how we fixed the notation. Okay, theta 1. And then you got a prismatic joint which will give motion like this. So here, we are now in the process of fixing the frames before further analysis, developing the link parameter table and all that. So I fixed one conveniently somewhere near the ground. It can be on the ground also as part of this base, which doesn't move. And then on this link, this is the first link. At the end of the first link, I fix frame 1. So O1. And uh, the one condition we were imposing, the DH convention imposes is the X1 is going to be a common normal between Z0 and Z1. Z1 is the uh, Z1 is the direction of motion, join the axis about which this moves, and this is vertical. It so happens in this particular case Z0 and Z1 are coincident, and the other axis is moving like this. This axis, this motion is like this. So joint axis Z2 will be like this, and Z1 and Z2. Well, we have taken them to touch at one point, but they are perpendicular to each other. That's how they are. Now, how do we fix X1 frames? The X frame, X axis. X1 we know is the common normal between Z0 and Z1 because Z0 and Z1 are collinear. We can draw X1 anywhere in this plane perpendicular to this line. Well, what we do for convenience is you have drawn X0 somewhere like this. You draw X1 because you have a choice of drawing anywhere in this plane. You draw X1 parallel to X0 so that to start with the angle between X0 to X1 about Z0, which will be theta 1, will be 0 to start with in this position at least. Next, as you move like this, the frame, we attach frame 2 to somewhere on Z2 where the common normal will be intersecting. You draw here, it so happens Z1 and Z2 are intersecting at this point. So common normal will be only in a plane perpendicular because they're intersecting at one point. So it can be either this way or this way. I choose it this way so that x2 to x1 to x2 angle will be 0 to start with, just for convenience. You can choose it anyway, but we try to minimize all these variables in the starting position. They're all going to move. Theta 1 is going to move once robot starts action. Okay, this in the home position, we are making like this. And then Z2 is like this. At the end of Z2, we fix the frame, which is sort of in the gripper. Okay. In the gripper, I fix a frame O3 and I make Z3 along this direction, preferably coinciding to be collinear with Z2, and the direction of x3 for this frame x3 will be perpendicular to the common normal to x2 z2 z3 because they're collinear. It can be anywhere in a vertical plane like this, but I choose it like this to be parallel to x2 for the same reason we mentioned earlier. Well, we fix our z3 x3 being like this, y3 will have to be like this, and direction of y can be fixed accordingly. Well, this is the, once we have fixed all these frames, now we'll try to develop what is A, alpha, D, and theta. Now for link 1. For link 1, what is A? A is the, we will take Di first. The distance from OI minus 1, that is O0, to to the intersection of X1 with Z0. Intersection of X1 with Z0 is at this point, and O1 is also at this point. O1 is at this point, intersection of X1 with Z0 is at this point. Therefore, I'm sorry, this is not O1, O0. This is O0. oi minus 1, o0 to this o0 to xi to intersection of z0 with x1. Well, that distance we decided to we call it as di, which is d1. So d1 will be, well, whatever is the length d1. Actually, this will be a constant for a RPP type robotom. In fact, this will be constant, this will be fixed. We fix them, they don't move. I'm sorry. Yeah. D2 is going to move, D1 is not going to change. Yeah. Then, so uh, what about AI? AI is the distance from the intersection of Z0 with X1 to O1. Z0 to X1 is this point. O1 is also the same point. So there is no distance between them. So the distance AI happens to be 0. So we write 0 here. Now, what is alpha I? Alpha is the angle between Zi minus 1 and Zi, or Z0 and Z1. Z0 and Z1 about X1, Xi, which is X1. But both are collinear, so there is no angle. So alpha 1 happens to be 0. Then the only thing is the d theta. This is a rotary joint. So theta 1, we don't make it as 0. We make it as a joint variable and leave like that. In this A, alpha happen to be zeros and D1 happens to be a fixed geometric constant for a given robotom, and theta is something that will be a variable for this R revolute joint. Next we come to, we need to fill up this. What is D2? D2 is the, mind you, this is a prismatic joint moving like this. So the distance between them, this keeps changing. So that will be a joint variable. Now, the D2 is the distance from O1 to intersection of X2 with X2 with Z1. Z1 to X2, X2 is here, Z1 to X2 is here. Up to that, from OI minus 1. For the case of 2, I is 2, therefore O1. O1 to this distance is your D2. And that D2 is some finite length. It will be actually a joint variable because this is a displacement. Okay. And the angle between and this distance D2, we said A2 is the distance from the intersection of Z1. This is Zi minus 1, I being 2, Z1 with X2, Z1 with X2 from this point to O2. But O2 is here itself. Again, therefore, your alpha is, rather A is 0. Link length, so called, happens to be 0. And now, what is alpha? Alpha is the rotation from Z1 to, this is Z1, Z1 to Z2 about X2. Z1 is upwards, parallel to Z0, Z1 is upwards, Z2 is like this. Positive rotation will take Z2 to Z1. So, but we need Z1 to Z2. Therefore, it will have to be minus, these two are 90 degrees. It will have to be minus 90. Alpha is minus 90. And again, so your theta is the angle between xi minus 1, x1 and x2 about z1. Well, anyway, that is going, because we have chosen them to be parallel to each other, it will be 0. So this is the how we complete the 4 parameters of the second link. Well, you can similarly complete the third link parameter, third row in the link parameter table. Then what do we do next? Well, what do we do is, we say this is the earlier homogeneous transformation matrix which we got by multiplication of two screw matrices, that is movement and rotation, movement and rotation. These two, when we multiplied, we got this homogeneous transformation matrix. Well, you substitute A alpha D1 theta 1, A 0 alpha 0 D1 and theta 1 is a joint variable, leaving that if you substitute in this matrix, you know what is theta, theta 1. Cos alpha is 0. So it will be cos alpha 0 means it will be 1. Cos alpha is 1. So minus sin theta. Well, I call it being for theta 1, I call it as just 1. C1 minus S1, again sin alpha, sin 90, rather sin 0, because alpha is 0. So this will be 0. Again, A is 0. So both elements are 0. So again, sin alpha is 0, cos alpha is 1. So this will result in this matrix. I call it as A1, which you can call it as H10. So that is what relates this frame to this frame. Similarly, A2 relates this frame to this frame. All you did is take these four parameters, substitute here, you will get this matrix. Similarly, A3 is, if you substitute these values, you will get in this matrix, you will get a similar 4 by 4 matrix relating O3 to O2. All you have to now do is multiply A1, A2 and A3, A1, A2, A3 in that order. You will get a relation between third frame to the base frame. That is what we call as H3, 0. Now we'll take one more example. This is a Stanford arm. It has got two rotary joints and a prismatic joint. This is rotary. This is also rotary. This can rotate like this. And this is a prismatic joint. Followed by, I have taken a, uh, a the RRR type of wrist, which are briefly represented this way. You got this actually, this is the link connected to this end of this prismatic joint, third link. And then you got these three joints. So anyway, first thing we need to do is assign, take the skeleton like this, assign frames like this. As I said, the first base frame, you have certain flexibility, but of course, axis is Z0. First joint axis will be your Z0, and about Z0, you're going to have theta 1. The next axis is like this, because this can rotate like this. About this axis, that is going to be your Z1, and theta 2 is the associated joint angle. Well, you can probably choose your x0 like this, in which case the common normal, the common normal x1 is going to be common between perpendicular to the plane containing z0 and z1. You see, this is like this and this is like this. In this plane, it is going to be x1. X1 is the common normal, and so on. As you go like this, you'll find that x2 is the common normal between this z1 and z2. They are in this plane. In this plane, x2 is the common normal. You can take up or down. It is your choice. Okay. Well, then we build like this. All these things, including only difference I would like to bring about, talk about in this case is we extend the frames attached to this joint and this joint and this joint. They will be at one part taken at the center of this wrist. In fact, they'll be so made that all the three wrist axes will be coincident at this point, and that is taken as a wrist center. And we fix all the three frames, O3, O4, O5, which are attached to this and these components. We bring them to this point called the wrist center. Though the frames will be different, the frames are attached to each of these motors or the joints, they will be coincident at one point, which is known as the rest center. Well, that's how we will carry out the analysis. Well, on the lines that we have, I have drawn these various axes like this. I will leave it as an exercise for you. You go through this picture, then you will find, and the lines is similar to what we have described in the previous case of the cylindrical manipulator. Only thing is, I have given the link, extended the link parameter table to this wrist elements also, the three wrist joints. Of course, right now, I have taken it as thetas as 0, but actually they should be 90. This is the first two are rotary joints, third is a prismatic joint. So therefore, these two will be theta 1, theta 2, though in this particular position they're shown to be minus 90. But once the robot starts moving, they should be taken as theta 1, theta 2. Third one is a link parameter, prismatic D3. D3 is a, these two will be geometric constants based on the construction of the robot arm. D3 will be a joint variable because that is one that is moving. So in parametric form where theta 1, theta 2, D3, this you can fix as minus 90 in this because that is not going to change as per the frames we have fixed. Again, the last three joints, though I have taken them as 0, you show them as theta 4, theta 5, theta 6. They will be the, because the wrist joints are also going to move to bring to any required arbitrary orientation. This is how we build the link parameter table for a 6 degree of freedom robot arm, which has got the 3 links and a wrist of 3 degrees of freedom. Well, for this what I have done is, in this particular case, I have taken the homogeneous transformation matrices for the first link, second link, and third link and multiplied all of them. I got H10 into H21 into H32. That will give me H30. That is the third frame. This is my O3, X3, Y3, and Z3. That to X0, X0, Y0, Z0. I tried to obtain that relation, the homogeneous transformation matrix. I didn't extend right up to the last one. By the way, the end effector from the wrist center to the end effector, we fix one more frame here, that is O6, and that distance is again fixed, and we call that D6. Okay. Well, to complete this, so as I said, I have taken H10, H21, H32 from the link parameter table by substituting that standard homogeneous transformation matrix, which is in terms of the 4 link parameters. And finally, I get this one. This as the H30. And as I said, that O3 frame in that Stanford manipulator I showed you now is like this, and our base frame is like this. If this is the case, the rotation matrix is like this. Is it? We can verify whether they are okay or not. Our X3, what are the direction cosines? It is the opposite direction of X0. So it will be -1. It has no components along this or this because perpendicular. -1, 0, 0. What about Y3 is along Z0. So it will be 0, 0, 1. Z3, third column, will be along Y0. So it is totally in the mid, 0, 1, 0. That's it. And then D2, D3, D1 happen to be the X, Y, Z coordinates of that point with respect to the base frame. Well, this is, I have done only up to the wrist center. Well, you can extend up to the final frame O6 at the end effector by multiplying this H30 with H43 into H54 into H65. Well, that completes the development of homogeneous transformation matrices and creating the necessary information for the forward kinematics using DH convention.